Number 5 has a set of hanging dice in a car. So it looks like there's the car here, right? And it's driving along a road, and inside the car are the dice. So we're looking at like a bigger version of the dice, but the car itself is accelerating from rest, if you read the problem, and it goes to 28 meters per second. So we know it's moving in this direction. And we also know it's increasing speed, so that's going to be positive. We know the total time that's elapsed is 6 seconds. We don't know anything about the position at all, and we don't know anything about the acceleration. We do know that they're asking you to find this vertical angle right there. So we have tension and we have weight. Where you don't know the mass is not given, and we don't know much of anything else at all. So when I do this, I'm going to break up my tension into 2 components. I need to do using my line of action. So I'm going to have my FTX and FTY. This angle is also this interior angle, so keep that in mind as well. So if I'm looking to find the angle, we can do that one of 2 ways. It's actually going to be in both my x and my y because I've got my components. So I've got ft sub x equals max, and I've got ft sub y minus weight equals may. So I know this acceleration is 0 because I'm not moving up and down. I've got ft, and then this is going to be cosine because it's the angle is adjacent to the y, so this is going to be cosine of the angle, and that's going to equal mass times gravity, right? That's what this is. Move it to the other side. In order to find theta, I would need to know mass. I know this is 9.8. I don't know tension. So where else would tension be? Tension is also here. So I'm going to do ft sine, right? So this angle, this one, if you look, is the x component is opposite. So it's going to be sine theta. It's going to be max. Well, so I don't know theta, I don't know ft, and I don't know acceleration, but I can find acceleration from my kinematic stuff. So I know initial velocity, final velocity, and elapsed time. So this gives me, I can use this kinematics equation, 28 equals 0 plus a times 6. So I actually can solve is 4.7 meters per second squared. So now I have something here. I still don't know mass, but the thing is, I know from experience that mass, if they don't give it to me, it means it's going to cancel. So I just leave it in as a variable. So I have ft sine theta. So now I've got 2 equations, and I've got the same two unknowns, or the same unknowns in both equations. So I'm going to combine the equations. Now, one little trick that I've learned is that when I do sine divided by cosine, we know that's equal to tangent. So one easy way to do this is just to take this entire equation and take this entire equation and divide them. And I'm going to put 9.8 instead of g. And what I get is the tensions actually cancel. Sine theta divided by cosine theta is tangent theta. The masses cancel, and you're left with 4.7 divided by 9.8 is 0.48. And if I do inverse tangent of that answer, I get a theta of 25.6 degrees. The other way you can do this, of course, is to do substitution. So you can do ft equals mg over cosine theta and substitute this expression in for tension, and you'll end up with the exact same thing. So you can do that as well if you prefer. All right, let's do number 6. A box sits at rest on an inclined plane, 30 degrees. Draw the free body diagram showing all of the forces. So Fn, we've got Fg, and we've got F static friction, which keeps it from sliding back down the plane. It said, how would the diagram change if the box were sliding down the plane? Well, if it was sliding down the plane, this would just be kinetic friction instead of static friction, but everything else stays the same. How would it change if the box were sliding up the plane after being given a shove? Well, the only thing that would change is that my kinetic friction now would be down instead, but the weight force and the normal force don't change. So that's it for number 6. Number 7. If the coefficient of kinetic friction between a 35 kilogram crate and the floor is 0.3, what horizontal force is needed to move the crate at a steady speed across the floor? And what horizontal force is required if the kinetic friction is 0? So you're on a horizontal floor. We know that the coefficient of friction is 0.3 because that's given. We know the mass of the crate is 35 kilograms. We're going to move across, that's going to be my line of action. We know we have a force that's giving it a push. We'll call that NP. And we have a steady speed. My interpretation of steady speed is that acceleration is 0, constant speed. So we're trying to find what is that force. So for the first part of this question, we want to know what that is in this situation. And then we want to know what happens if it's frictionless. So let's draw a free body diagram. Okay. We have our motion diagram. So now all we have to do is we're looking for this force on the X. And I want to make sure that if I'm using the net force, that I'm using the equation that will give me what I'm looking for. So if I'm looking for this force, then in order to do that, I need to know the acceleration and I need to know the friction force. Well, I know acceleration is 0. Friction force I know how to solve. So friction force is mu times normal. We're given what mu is, so all we need is normal force. This normal force is on the y-axis. So I'm going to solve for my y-axis. I know it's not accelerating up and down. This acceleration is 0, so normal force is mass times gravity. So if I put that in here, 0.3 times 35 times 9.8, I get 0.3 times 35 times 9.8 is a force of 102.9 newtons. So this force, when it's at constant speed, is 102.9 newtons. Okay. So B says, what if there is, what if this goes to 0, right? What force would be required? So the answer is no force is required. If you have no friction, then it's going to maintain an acceleration of 0 without any force, right? Because if you look back again at your net force equation, F and P minus FFK equals MAX. If acceleration is 0, and your friction force is 0, then you end up with a normal force, a pushing force of 0. None is required to maintain motion on, right, at constant speed on a frictionless surface.